So let's see what we've got so far. We've showed that formally, if you have the y that just jumps up from nothing, teleports to initial position, and then oscillates, that solves the differential equation where the right-hand side is my naught delta prime. And that's technically sort of all we need to show. But then we looked at trying to do this without doing it instantaneously and without teleporting. And we said, well, what if the f was just a hump and then another hump like that, or a rectangle and then an opposite rectangle? And it does seem to be doing the right job in this differential equation. But what we really should show, apart from the differential equation completely, is just something perfectly, purely, let's say, about delta prime. Is it true that delta prime can be thought of as an appropriate limit of hump and then opposite hump? Okay, so let's actually show that independent of its connection to springs and things like that. All right, and there's various ways you could do this. I don't think the way I propose to go through this in the handout is the absolute tightest way in terms of fewest number of steps, but I think it's nicely intuitive. Okay, so what we need to show is that if we pair that with a test function, that's the same thing as paired with a test function over here. And remember, phi can be assumed to be as nice as we want. We've already discovered that we're pretty sure that we want to assume all test functions are infinitely differentiable. And at least, let's say it's C2. In other words, its second derivative is continuous. And that's far less than we really assume about phi. It's probably more than we absolutely would have to assume about phi to get this to work, but I didn't really think about maxing it out, and that's not the point. So we've got this function, the f, oh yeah, this is dotted. We got the f epsilon, and notice the height here. What was the definition of f epsilon? Right, f epsilon of t was, let me just get the factors right. It was plus or minus my naught over 4 epsilon squared, plus here, minus here, and of course 0 elsewhere. And so it's over epsilon squared. So when this squeezes down, it doesn't just get tall in such a way to keep the area constant. That's how delta functions get made. It's jumping up faster than that, and so the area is actually going to infinity, and that's going to be crucial. Okay, so let me just get back to my my cheat sheet here. Okay, so let's look. Well, maybe I can leave that together. The first thing is just a basic thing about analyzing the integral of some fairly random function phi. We don't know that much about phi. It's just any C2 function over this interval. And the key is I want to claim that it's basically essentially evaluating phi at that middle and evaluating phi at that middle and taking the difference. And what happens when you take the difference of two values close together of a function and divide by an appropriate constant? We should be getting something about phi prime. And remember, we know what this is supposed to be. This is supposed to be minus m naught y, phi prime of 0. So we'd like to say that this integral and this integral, when you squeeze down, converges to just taking a difference of two values of phi and hopefully divided by the 2 epsilon that's in between there. Okay, I didn't have to pick the midpoint, but it's the most natural thing to pick. Okay, so we just really need to go back to the midpoint rule and do a tiny little derivation of the error estimate for the midpoint rule. Okay, so the integral from, let's say, a minus h to a plus h of some reasonably nice function, in particular a C2 function, dx. Okay, the midpoint estimate on that, okay, so if I'm going from a minus h to a plus h, I'm taking the midpoint estimate on that sucker, and so I'm just making a rectangle with height f of a, and the width is 2h. Okay, so there's that estimate. Okay, but it's going to be crucial to know how accurate that estimate is. What's the error bound? Okay, so let's use Taylor's theorem. That's one of the most basic ways to get a local estimate of a function from very little information about that function. Okay, so let's just suppose for a second one more thing about f. It's not just some arbitrary twice differentiable function. It's got an actual bound. Ooh, you know, I'm using t's. Let me use t's. Yeah, let me use t's. Sorry. I know I go back and forth between t's and x's, but I like t's when we're thinking about the springs and things. Okay. Let's suppose it has a known upper bound on the size of the second derivative. It can't be that wiggly. It's not too very different from a straight line on this interval. Okay. And let's use Taylor's theorem to get some idea of how good this estimate is going to be. Okay. So Taylor says that the difference between the actual value of f of t and its, ooh, and I think I missed a parenthesis in here in my written solutions. I'll try and fix that. There's the straight line approximation. There's the difference, the error between the actual function and the straight line approximation. Taylor says that that's less than m over 2 t minus a squared, which kind of looks like what would be the next term in the Taylor series, but with the m, the upper bound on f double prime put in instead of f double prime itself. Okay, so that's kind of the theoretical calculus fact we need to know here. And we'll see if we want to go back to that level, but I'm going to assume that that's something we're confident with. Okay, and now we're going to integrate. Okay, so the integral of this error, and this really turns into a minus sign. The reason I didn't notice this error is that's going to die very soon. dt. Okay, so that's less than or equal to the integral of the absolute value. Oh yeah, so here's the absolute value. So the size of the integral of the error, I really want to get something that says something about f of t. And the trick is integrate something you know is small, use the triangle inequality, and then separate it out to isolate the part that you want to do. This is a technique we've used once before. Okay, so the size of the integral of this error is less than or equal to the integral of the absolute value, just putting the absolute value in. That's the triangle inequality for integrals we've talked about before. And then use this guy. And of course, the value of the absolute values a lot of the time is to make sure we know which way inequalities go. That's what happened before as well. Okay. That's an explicit function, and I can totally take the integral of that. It's easy to calculate that that's m over 3 h cubed. Okay. Alrighty, so, but what is this guy? Okay, let's see if I can get away with just putting it up here for a sec. I want to keep that. Okay. The integral from a minus h to a plus h of all this stuff, f of t minus f of a minus t minus a, and again, that's a sign that's currently, as I look at it right now, that's a sign that's wrong in the solutions. Okay. Okay. The key thing is that it's a symmetric integral. This t minus a part, if I go symmetrically around a minus h to a plus h, if it were a straight line, this straight line part absolutely just cancels out. If you want to do the antiderivative and see it cancel out, you can, but it's geometrically because it's same going down here and going up here. Okay, so it's as if I just had this guy. It's a very common argument about the midpoint rule. That's why I use the midpoint rule, because that's why it's actually a nice approximation, a particularly good approximation. So this is really just the integral that we're interested in, and then minus exactly the integral of that constant value at the middle, which is the approximation. So in fact, this absolute value is just the absolute value of the difference between what we really would like to calculate but we can't, the integral of f, and our approximation. That's our error bound. Boom, there it is. Okay, so this is less than or equal to this guy. Okay, so now we've got a little bit of control over that that idea of using a midpoint. So now we go back to our actual situation of F epsilon. Okay, so let's see, limit epsilon goes to 0. F epsilon acting on some nice function phi. Okay. Oh yeah. So that's good. I thought I'd skipped something, but no. Okay. And here's that factor in front. Here's the 1 over epsilon squared, which is going to be really crucial that that's exactly the right way that should grow. And we saw that already from a physical point of view in terms of like acceleration. It canceled out the acceleration and the time factor in the right way to give exactly the right y naught endpoint of our little two-stage journey of getting accelerated and decelerated. Okay, because it's just a couple of rectangular pulses, this is what happens when you integrate it against the test function. You just get the integral of phi in one and 1/2 minus the integral phi in the other half. And now we're going to use that. We're going to approximate these guys with the midpoint rule, but then put in an error term and show that the error term goes to 0. Okay. Now, can we use that result? Well, if phi is C2, okay, phi double prime is a continuous function on a compact interval, a finite closed interval, and so this guy, all the values of phi double prime of t are less than going to be less than or equal to some m for all t in, let's say, there's some minus some interval on which we have an absolute bound. Okay. Let's say minus c and c are way out here, and they're fixed. And I'm just going to make sure that epsilon has gotten small enough so that minus 2 epsilon are within there. Because we only care about epsilon going to 0. And so eventually they're within any fixed value. So we just pick some c, like 1 or something like that, figure out the maximum of phi double prime. That m is going to go into the estimate. But the main thing is there is such an m. And I'm going to do bad board style because I have my little small board, and I'm going to erase what I just wrote. Okay, the main thing is we will be able to use the error estimate that we had to assume to get Taylor to work. Okay, so let's just work on this for a second. Okay, ignore this for a minute. Just work on this, those actual two integrals put together. We're going to use the midpoint estimate. So that's going to be 2 epsilon is the length of that interval. It's also the length of that interval, so we'll get a common factor. And we're going to get phi at the midpoint of that guy, and then minus phi at the midpoint of the other guy, which is epsilon. But then plus, and I'm just going to call them R1 of epsilon plus R2 of epsilon. They're just the remainder terms. Okay? And the key is that our error estimate has shown that the size of both of these guys is less than or equal to some constant, happens to be m over 3, times epsilon cubed. And that cubed is crucial because even when we divide by epsilon squared, it's going to be good. Okay, so that's going to say, oh, really bad board style. I'm going to stick this in this blank space, and then I'm going to rewrite the board. Okay, it says that the limit as epsilon goes to 0 of the combined error, all this other stuff that we don't really want to care about over epsilon squared is 0 because it's going to be less than m over 3 epsilon. Okay, therefore we can totally ignore it. And now moving back to our whole package with the epsilon squared in the denominator and everything, that's going to be m y naught over 4 limit epsilon goes to 0 of 1 over epsilon squared 2 epsilon phi of minus epsilon minus phi of epsilon. Now this isn't quite what you usually see for derivatives. Well, let's see. So the epsilons cancel. That's crucial. This 2 cancels this down to a 2. Okay, and this is taking the function phi and evaluating it not at 0 and h, but at minus epsilon and epsilon, but still doing a secant slope. Okay, this is still going to be 1 over 2 epsilon, times a secant slope. If you insist on relating it to the standard kind of less symmetrical definition of the derivative, it's not too hard, so I'll just do that step. So we get an my naught. I'm going to leave the 2 out though. Okay, and I'm going to take a minus sign out. We'll see why in a second here, because this is going from the left and minus the right as backwards, so I'm going to correct that with the minus sign. And I'm just going to take this out, and I'm going to do a little trick of putting in the value at 0 twice, adding and subtracting the same thing. It's a pretty standard trick. So if you're thinking, I'm not sure, this, I know it looks like a secant slope, and it looks right, except for the minus sign, but is this really right? Oh, and that's a minus epsilon. I think there's 3 parentheses in there. It's hard to fit them in. Okay. All I did was I added and subtracted phi of 0 and strategically. Okay. That is definitely the derivative of phi at 0. Okay. And that, if you just do a little change of variables and let h equal minus epsilon, then h is going to 0 from the other side, is still the derivative. It's just with a change of variables. Okay. And then that's just going to be minus my naught phi prime of 0, which is, as advertised, delta prime acting on phi. Okay. So I like this argument. We had to do a fair amount of detail to do it, but it's really great stuff for reviewing things like Taylor and things like integral estimates, really, really simple integral estimates, and this fact that if you look at, it's the lemma here that we just showed basically, and with the minus signs not screwed up, it's that if you take a symmetrical version of the derivative and do those tangent lines, that is phi prime of 0. If phi prime of 0 exists, there's a subtle thing that this, you can get examples where this guy exists and phi prime doesn't really exist because it's a little too nice and too special. But very often this is a nicer way to take the derivative. In fact, it's a more stable numerical way to take the derivative than the usual one-sided way. Okay, so that was nice because I wanted everything to be symmetrical. I just think it's prettier. We didn't absolutely have to have this idea where we symmetrically pushed it up and then pushed it down, but I tried an asymmetrical way and it was ugly. I thought it was ugly. So I think this is prettier. Okay, so now we've seen in about 3.5 ways probably that this delta prime really comes in here. And if you want to move something really quickly, the punchline, to move, and I'll finish this video with this guy. I should be able to, I hope, easily finish the handout with the next video. To move an object quickly, use delta prime, which is the limit, the idealization of an up pulse and a down pulse. You know, hit it with a hammer, then, oh gosh, it's moving, I want it to stop, hit it with symmetrical hammer once you've gone halfway, and that's going to be the delta prime. We're going to investigate a tiny bit more about delta prime to finish the handout in the next video.